Okay, let us begin with our lecture today, Quantum Field Theory 2. We are in the middle of quantizing and discussing the quantized Yang-Mills theories. And last time we started with looking at higher orders and renormalization. And we already wrote down the so-called renormalization transformation, which is a recipe that gives you a certain counter-term structure, which hopefully is able to cancel all the divergences which appear in the course of the calculations. But we have not yet established that they do. But in order to establish it, the next tool that we need are the Slavnov-Taylor identities. So let us now discuss Slavnov-Taylor identities. The Slavnov-Taylor identities are nothing but the expression of BRST invariance on the level of green functions. You know that after gauge fixing and adding ghosts, the Lagrangian has a new symmetry, BRST symmetry, and this symmetry on the Lagrangian level is reflected by certain Taylor identities are nothing but the expression of BRST invariance on the level of green functions. You know that after gauge fixing and adding ghosts, the Lagrangian has a new symmetry, BRST symmetry, and this symmetry on the Lagrangian level is reflected by certain relationships between green functions, and those are the Slavnov-Taylor identities. The Slavnov-Taylor identities are very general, and you have already seen many applications of them, and you have already seen many concrete Slavnov-Taylor identities coming out of explicit tree-level calculations, which were then used to derive the unitarity of the S matrix or to establish Lorentz invariance or some other important properties. But now we discuss the general formalism, where they come from in general, how they are derived and how they look like on the level of full green functions, including higher orders. And then at the end of these sections, we will also see how the concrete identities that you have already seen, how they emerge from the general structure. So let us begin. As I said, we have a symmetry of the Lagrangian, and if the path integral measure is invariant, then we immediately obtain those Slavnov-Taylor identities. And we know at least one case where the path integral measure is indeed invariant, namely if we use dimensional regularization and if we are in D unequal to 4 dimensions. Then this is already established. So here, if we have a BRST invariant classical Lagrangian, remember that I now introduced the symbol L classical, CL, for the Lagrangian which does not yet have counter terms. Then this is BRST invariant, S of L classical equals 0. Then from this general formalism we immediately obtain Slavnov-Taylor identities which look like this. In symbolized form, 0 is equal to the BRST transformation in quotation marks of green functions, where I already explained that I use this as an abbreviation of the sum of all green functions which you obtain by doing the variation of each individual field turn in turn. And so the green functions here that satisfy this are the green functions which you compute by using the Feynman rules from this L classical Lagrangian. In other words, these are the green functions that you obtain without counter terms. These are the so-called unrenormalized green functions, which certainly contain ultraviolet divergences, but as long as D is unequal to 4, they are well defined and can be computed, and for any D unequal to 4, they satisfy these Slavnov-Taylor identities. So let's write this down. These are the green functions computed from L classical without counter terms.
طبعا علينا أن نعرف أن الجرين فانكشن هي ما هي إلا معادلة الطاقة العالية. يعني تعريف الجرين فانكشن في نظرية اليوسف هي معادلة الطاقة العالية. طيب أي معادلة الطاقة؟ تعال نشوف. هذه هي المعادلات. طبعا عملت فيها فيديو في هذه السلسلة، هي ذكرت فيها تصريحا أن معادلة جرين هي معادلة الطاقة العالية. فهذه هي معادلات الطاقة. المعادلة الأولى بتخص الكتلة والجاذبية، المعادلة الثانية تخص الشحنة وقانون كولوم أو القوى الكهرومغناطيسية. نجد في هذه المعادلات أن المقام أكبر من البسط، وهذه المعادلات عبارة عن كسر أو أرقام تمتد من الزيرو إلى الواحد فقط، من الزيرو إلى الواحد، لا تفوت الواحد. إذا فاتت الواحد فإن الفضاء ثنائي الأبعاد يفعل آلية الدفاع النفسي ويدافع عن نفسه. لهذا نجد أن هذه المعادلات عبارة من الزيرو إلى الواحد فقط. تمثل معادلة جرين.
So-called unrenormalized green functions. So they satisfy this Slavnov-Taylor identity. And then let us also look at the renormalized case, namely if we use the full Lagrangian including counter terms, which we called L bare or L classical plus L counter terms, then this satisfies a new BRST symmetry, namely this S renormalized acting on this equals 0. And then using the same general argument, we get, of course, 0 is equal to this L S renormalized of renormalized green functions is also 0. So these are now the renormalized green functions from L classical plus L counter terms. We do not yet know whether those green functions are finite, because we have not yet established that the counter terms are able to cancel the divergences. But anyway, if we define the counter terms in the way we did, then we know the bare Lagrangian is BRST invariant, and therefore we know that the renormalized green functions satisfy again such a Slavnov-Taylor identity, where the BRST transformations are modified by renormalization constants in the way we discussed. So, and just to make this clear, this is fully established. There is nothing to prove anymore. We have given the explicit proof of this in dimensional regularization. Just to be safe, we should keep d unequal to 4, because we do not know whether the limit d going to 4 exists. But in this sense, it is fully established. And if it turns out that the limit d going to 4 exists, since the 1 over epsilon poles cancel, then of course this remains true also for d equal to 4. Then we have established the Slavnov-Taylor identities for the renormalized theory. Okay, and now I just want to show you a concrete application of the Slavnov-Taylor identities. So this is the general thing, and what does it have to do with the concrete identities that you have already seen a few times in the lecture and in the exercise? Let us just look at one single example, namely the relation for the photon or gluon self-energy. As an example application. So we define the full photon propagator with all Feynman diagrams and two external, let's say, gluon fields. Did I say photon? I'm sorry. So gauge field 2-point function, with two gauge fields, A mu A and A mu B. And the full green function including all possible Feynman diagrams, not necessarily one particle irreducible. And let us see what kind of Lyapunov-Taylor identity this object fulfills. For simplicity, let's do it without counter terms. Even though with counter terms the structure would not really change at all, but just to have a concrete notation, let's do it without counter terms. All right, let me immediately show you the Lyapunov-Taylor identity that we need in order to get information on that. It is the following. We take 0 is equal in quotation marks to 1 such BRST transformation of a green function in quotation marks. And which green function should we take here? Let us take this one, C bar A of x, B of y. Okay. So this is a green function here, or an expectation value of an anti-ghost field and the auxiliary field B. And then this expression in quotation marks, as I said, this is just a shorthand notation for the following, namely for what is it a shorthand notation? We now take the BRST transformation of all the individual field operators and add them up. So the first term is BRST transformation of C bar at x times BB at y. Then we need to anti-commute the BRST operator with C bar because they are both fermionic. Then we get minus C bar at x times the BRST transformation of B at y. And that's it. So this is what I mean by this abbreviated symbolic notation. Expectation value of an anti-ghost field and the auxiliary field B. And then this expression in quotation marks, as I said, this is just a shorthand notation for the following, namely for what is it a shorthand notation? We now take the BRST transformation of all the individual field operators and add them up. So the first term is BRST transformation of C bar at x times BB at y. Then we need to anti-commute the BRST operator with C bar because they are both fermionic. And then we get minus C bar at x times the BRST transformation of B at y. And that's it. So this is what I mean by this abbreviated symbolic notation. And that is the Lyapunov-Taylor identity that is guaranteed to hold. Now, what is that actually? What is the BRST transformation of the anti-ghost? Who knows it? You know it? Yeah, it has something to do with A. In fact, it is equal to B, and B has something to do with A. So that was this BRST doublet that was introduced at the end in order to write down BRST invariant gauge fixing term. And that was defined to be BA of x. Then we have this. And the BRST transformation of B was 0. That was the so-called BRST doublet. S of C bar is B, S of B is 0. So here we get 0. That is our Lyapunov-Taylor identity for the two-point function of the gauge field. So what is the identity? 0 is equal to this green function. That's it. That is our Lyapunov-Taylor identity. Let's write it down. So this holds at all orders in dimensional regularization, and that is guaranteed. Maybe to stress it once more, we are using here the path integral definition of time ordering. So as I told you in the beginning, there is a slight difference at singular points between the path integral of the time ordering defined via the path integral and via theta functions in the operator formalism. And all of this holds in the sense of the path integral time ordering, using time ordering of the path integral. Okay. So this is our Slavnov-Taylor identity. Now, as you might see, this is not really yet an identity for the two-point function of a mu, a nu. So we have to rearrange it a little bit. And the rearrangement that we now do is not really a Slavnov-Taylor identity as such, but it is a different identity. But this is the core, and from this we will derive our interesting information on the a mu. So what is the relation to a mu? That goes via equations of motion, or these Dyson-Schwinger equations that we have also introduced. So in a way, this is a tip. Let's nevertheless derive it really from the path integral in the way we did it. Namely, we take a total derivative in the path integral d by db a of x, total derivative with respect to ba in the path integral of the following, of bb at y times e to the I times the action. And we are using the classical action at the moment. Okay. So this is 0. As we discussed, and such equations yield Dyson-Schwinger equations, or in other words, relationships for green functions involving equations of motion. And okay, so let's evaluate it. Let's factor out the usual exponential, and then in front of the exponential we have two terms. One term comes from taking the derivative of b with respect to b. That gives a delta function, Kronecker delta ab, times a four-dimensional delta function of x minus y. And on the other hand, we get a term from the product rule, from taking the derivative of e to the I times the action. Then we have the prefactor bb of y, and then times the derivative of I times the action with respect to b, and that gives the equation of motion of b. And that was what you had in mind maybe, namely the equation of motion relates b to d mu a mu, like in the gauge fixing. And that is what we now get. So we get here times I, and then times the equation of motion. The equation of motion is, if we take the derivative, psi times ba plus d mu a mu. And we have this equation of motion. So, and then we have here three terms. The sum of three terms is 0. The first term is a delta function. The second term, if you evaluate the path integral, this gives a green function bb. And the third term is a green function b and a. So let's write it down. Evaluating the path integral gives then this, Kronecker delta times a delta function, x minus y, plus the green function times I of ba at x, bb at y, plus I times psi times the green function d mu a at x times bb at y. So that is what you see from this equation of motion or Dyson-Schwinger equation. You can replace B by its equation of motion, but the green function with B or with its equation of motion is not exactly the same, but you get an extra term involving a delta function. This is the typical thing from these Dyson-Schwinger equations. Okay, now we can plug in our Slavnov-Taylor identity, which tells us that this is 0. That was what we have derived before. And then we see that that green function here between A and B gives just the delta function and nothing else. So maybe we can write it also in Fourier transformed form. Then we get 0 is equal to delta AB, just the Fourier transformation of a delta function into momentum space gives just 1, and then plus I times psi times the Fourier transformation of the green function here, let's say Fourier transformation evaluated at some momentum flow P. What does that mean in terms of Feynman diagrams? So in terms of Feynman diagrams, we can write down that green function here, I times psi, and then we have here a green function between A and B. This is basically a green function. On the one hand side we have AA mu, then we have all Feynman diagrams, and then at the end we get BB. And there flows a momentum through it, P flows through the green function, and the A mu is taken derivative of. In momentum space, d mu becomes minus I times P mu of the momentum which flows into the A field. Okay. So in this green function here, apparently is equal to minus Kronecker delta AB at all orders. Now, the right-hand side here is an exact expression which contains no higher orders. It is a tree-level expression. It is just a lowest order expression with no higher orders in the coupling constant in perturbation theory. That means all higher order corrections vanish. That means here on the left-hand side, in terms of Feynman diagrams, there will be a tree-level graph, a one-loop graph, two-loop graphs, and so on. And that means the tree-level graph must be equal to this, whereas all the higher order correction Feynman diagrams must be 0. That is the result of this equation here. So at tree level, it means, let's say, psi times P mu times a green function, tree level green function, between A and B with no loop in between is just minus Kronecker delta AB. That means this green function here has the following value. Which value does it have? It must have the value P mu divided by P square times 1 over psi. Okay. Because then if you contract with another P mu and multiply by psi, you get minus Kronecker delta AB. So, and this green function exists. So it's an unusual green function. It's like a propagator Feynman rule, but it's a propagator which connects two different kinds of fields. And that is possible. I told you that in general, the propagators in Feynman diagrams, they are the inverse of the differential operator in the Lagrangian. And that is to be understood in a matrix sense. If we have many fields in the Lagrangian, like A, mu, and B, then the differential operator is a matrix in the space of all those fields, and the inverse matrix can have off-diagonal components. This is such an off-diagonal component of the inverse of the differential operator. And so we have here such a tree-level two-point function, in other words, a propagator between two different kinds of fields. This is nothing to worry about, and one could immediately calculate it from inverting the differential operator. But here we get the result from the Dyson-Schwinger equation. Okay, so this is the result for this tree-level Feynman graph. Yes, please. Yeah, Fourier transform of a delta function is 1. Right. Well, exponential of yeah, okay, but we split that off. So Fourier transformation with respect to this exact argument x minus y, then this is just 1. No, but we split, the variable in the Fourier transformation is the difference x minus y. We do not do an individual Fourier transformation with respect to x, but directly to x minus y, and then the Fourier transform of that is 1. Indeed, if we were taking a Fourier transform with respect to x, then we would get e to the ipy maybe as a result. If we would take a Fourier transform with respect to y, we would get e to the ipx in the result. But if we take Fourier transform with respect to x minus y, we get 1. Okay, now let's look at higher orders.
طبعا هنا دالة جرين تساوي الدلتا، وهذا يحقق ما قلته أن الطاقة الكلية، الطاقة التي ذكرناها، طاقة الجاذبية والطاقة الكولومية، يجب أن لا تفوت الواحد. طيب بعد إذا فاتت الواحد ماذا يحدث؟ يعني سيحاول الفضاء صناعة بعث الدفاع عن نفسه مباشرة. فدالة جرين تساوي الطاقة معادلة الطاقة لهاليوسف، ويجب أن لا تفوت الواحد. إذا فاتت الواحد الفضاء صناعة بعث سيدافع عن نفسه ويجعلها أقل من الواحد مرة أخرى. وهذا أيضا تتفق مع نظريتي.
Higher orders, this combination here has the following structure. So what are the loop graphs contributing to a green function with external A and external B? If we have the following propagators and propagator Feynman rules available, we have now, as you see from here, we have an unusual Feynman rule available where a B directly connects to A with a tree-level propagator. But of course we also have ordinary gauge boson propagators available. But we do not have available a propagator B to B. That is not available because that is 0. So the only two interesting propagators which appear are this one and that one. That means the only thing an external B can do is to go into A. That's absolutely the only possibility. So therefore, in every Feynman diagram, no matter how complicated it is, the external B that starts at this point has only one possibility. It can only turn into an A. And then either this is immediately the tree-level graph and the whole Feynman diagram ends here, or the A does now something complicated. And so all the higher order graphs must have this structure. B goes to A, and then A does something complicated, and at the end we get another A. And therefore, we now see all higher orders. We now see that this building block here must be 0. And this building block is a full all higher orders. Photon two-point function times that object times minus p mu divided by xi over p square. Okay, and so that must vanish, and so we see from this that the contraction of the two-point function with two external vector bosons times p mu vanishes. That is the essential point. So in other words, we already had introduced the self-energy sigma mu nu AB of two gauge fields, that if you contract it with p mu, then this must vanish. That is the outcome, and that is the impact of this particular Slavnov-Taylor identity plus equations of motion. We see that the gluon self-energy must be transverse at all orders in perturbation theory, at least in dimensional regularization at d unequal to 4. And this is something that you should also calculate as an exercise, and hopefully at the one loop level, and let's see in the afternoon whether it worked or not. But that is the prediction, that at all orders the gluon self-energy is transverse. And it is an example of how you can derive Slavnov-Taylor identities for concrete green functions of interest from the general recipe. Okay, any questions to this? Yeah. No, it's not. I mean, you are completely right in picturing it as an abbreviation for its value from the equation of motion. And so it's here really a kind of artificial tool which we use in order to simplify the derivation of Slavnov-Taylor identities. In principle, it could also be possible to completely eliminate the B from all equations entirely, and then the Slavnov-Taylor identities and BRS transformations would take a slightly more complicated form. Deriving such identities would be a little bit maybe more cumbersome, but the final result must always be the same, absolutely the same. But here we use it as a tool, and so that is the way I would use it also in practical calculations, namely as a tool to simplify the discussion of BRST symmetry and to simplify the derivation of Slavnov-Taylor identities. But as you see here, at one place of the derivation we do exactly what you have in mind, namely we eliminate the B by using its equation of motion. However, there is one trick which is a little bit subtle, and which is this equation here, namely you cannot just always replace B by its value from the equation of motion with no other modification, because then you would not see this delta function here. That is the only thing that you need to take care about. And so here, that's why we started with a path integral derivation of this equation of motion relationship. And so you see that here in principle, if that were 0, that is also 0, then you would say, okay, the green function with psi times B is the same as the green function with d mu a mu, which means you can replace it by its value from the equation of motion. But it's not the same because of that delta function. And this delta function is again coming from the singularities where at equal space-time points there are singularities. And so that is an extra term that you need to take into account. And this extra term appears exactly only in one place of the entire theory, namely in this case. in every other green function, so if you would take anything else, not B here, but any other field, then the derivative with respect to B would just be blind to those fields, and there would not be a delta function, and then you would derive an equation exactly like you have in mind, namely a green function with lots of fields, and 1B is the same as the green function with lots of fields and d mu a mu. So as long as you have green functions with just one B, you can replace B by its value of the equation of motion. But only in this case, there is a difference, and this is the one that we used here to derive identities. So, but B is completely unphysical, and it's just a placeholder and an abbreviation which can be used in equations like these. Yep. Because our derivation of these Slavnov-Taylor identities is completely independent of the loop order. So that's just an exact relationship for the full green function, and the special case is the tree level. So tree level behaves in a special way, but everything else is uniformly treated here, subsumed in this equality. Yep. That was this point here. So, okay, you can also explain it in a few other ways, but it was here. That green function, whatever it might be, times p mu gives a delta function. And then I said, okay, that must mean that this green function here has this value proportional to p mu divided by p square, because now if you contract with that p mu, you get 1. Right, that was this place. From it was already here, and it came from the derivative d mu a mu. And there is also another thing that you can say, namely from Lorentz invariance alone. If you have such a green function in momentum space, then because we are in a Lorentz covariant quantization, so then we know that this must behave in a Lorentz covariant way. It has one Lorentz index, it depends on one p, so the only possibility is that it is proportional to p mu times some function which might depend on p square. So that is also clear from Lorentz invariance alone. And then if you know this together with that, then this is the unique answer. You could have asked also another question, so let me point you to that other question. Namely, you could have asked yourself or me why the derivation was different from the derivation of transversality of the photon self-energy in QED. Because we derived already that the photon self-energy is transverse. We used it in quantum field theory 1, and we also derived it here some weeks ago. And that derivation was different from this one. So you can now think about that at home. Not now, but later maybe. What happens if you apply the QED derivation to this case? And I hope we will come back to that. Maybe I will tell you the resolution of that paradox in a few weeks, I guess. That's all. In other words, the derivation in QED was more straightforward than here, and that same derivation doesn't work in non-abelian gauge theories. But the result, nevertheless, also holds, but one needs to use that other derivation using the B field. Now let us go to the next topic. I have now explained to you how the Lyapunov-Taylor identities work. I have given you one example, and of course there could be infinitely more examples. But this single example is, I think, enough to explain the sketch of the renormalizability proof. So as you probably know, non-abelian gauge theories like QCD or the electroweak standard model, they are renormalizable, as we call it. And establishing this was a big step in our understanding of nature. And so let me give you some names. Hooft was the first who gave a renormalizability proof of those theories. Then there were important contributions by Lie, Zinn, Justin, and in the end also BRS, using BRST symmetry. And it works by induction. And let me sketch the two steps of such an inductive proof of renormalizability. Let us first assume that the theory is already renormalized up to order n-1. So that would mean loop order n-1. Using the renormalization transformation of our section 261, where I gave you the recipe how to generate counter terms by doing this transformation. Gauge coupling goes to Z times gauge coupling, fields go to square root of Z times the fields, and in this way you generate a certain structure of a counter term Lagrangian. And we have up to order n-1 loop determined the counter terms from that Lagrangian such that the theory has become finite. So that means we have obtained L counter term up to this order. That is equivalent to having a bare Lagrangian up to this order. And these renormalization constants delta Zi up to this order, they are all defined. And we assume that the green functions are finite. That means the limit d equal to 4 exists at the order n-1. And that includes the green functions needed for the Lyapunov-Taylor identities. For the Lyapunov-Taylor identities, we need green functions where these operators corresponding to BRST transformations appear. So, and then S renormalized of phi, those are these renormalized BRST transformations. And they are so-called composite operators. They involve products of operators at the same space-time point. So there are special Feynman diagrams for those green functions, and they involve extra divergences on top of the normal green functions. And we assume that they are also finite, and the ordinary green functions, they are finite too. Needed for the Lyapunov-Taylor identity. So they are all finite. And we also assume that the Lyapunov-Taylor identity holds. But that is not a necessary, the assumption is not needed, because we have already proven that if we define the counter terms in that way, then the Lyapunov-Taylor identity definitely holds. Anyway, I write it down here it's a necessary ingredient for the proof. So, and first of all, this is clearly possible at tree level, where n minus 1 equals 0. And so therefore there is a beginning to our inductive proof. And so now we assume it for n minus 1 bigger than 0. And then we do an induction step. Okay, so that is just a sketch of the proof. So let us imagine what one in principle has to do. What one has to do is you now go to the next order. You go to the order n loop, and at the order n loop, a renormalization must cancel the appearing divergences. So you need to study the structure of the possible divergences. Study the most general possible structure of appearing ultraviolet divergences at the next order, order n. And how can such a study proceed? You want to study it without actual calculation, of course, because we want to do it for general n, so we cannot do actual explicit computations. We must study it on the basis of general principles. So what are the principles that we have available in order to study the general possible divergences which could appear at any order n? One principle that we have available is that what we have just seen on the previous blackboard, namely the Slavnov-Taylor identity. For example, for the photon self-energy. We have just seen that the photon self-energy is transverse at all orders of perturbation theory before doing renormalization. That means including the divergences. So the divergences of the photon self-energy are of course also transverse. So we know already something about the possible structure of all divergences. If you contract the divergent part of the photon self-energy with p mu, you get 0. Things like this can be obtained from the Slavnov-Taylor identity. So one thing for sure is the divergences are restricted by the Slavnov-Taylor identity. For example, the gluon self-energy, sigma mu nu, for example, including the divergent part, times p mu gives 0. Okay. That is a restriction. And of course, now the point would be, and your task, if you would carry out the proof, then you study all such restrictions of all divergences following from the Slavnov-Taylor identity. And that was done exactly in those proofs. So the second thing, divergences are always restricted by the general theorem of renormalization. The general theorem of renormalization tells you that if a theory is finite up to order n-1, then at the next order n, the divergences are so-called local. They are in momentum space polynomial in the momenta and not other functions of the momenta. So they are polynomial in the momenta, and the degree of the polynomial is also known. Namely, the divergences of one particle irreducible Green functions is a polynomial in the external momenta, and the degree of the polynomial is the degree of superficial divergence of the green function. Okay, so this is completely known by the general theorem, and just as a reference, this general theorem of renormalization was explained, for example, in our Quantum Field Theory 1A lecture 2019. That was lecture 11 and 12 approximately, and it was also explained in the multi-loop lecture. Basically lecture 1 to 10 that contained essentially the full proof of this. Okay, so there are two restrictions, namely in momentum space polynomial of a certain degree, and the degree is
طبعا الملتي لوب سيريز، يعني هذه السلسلة إن شاء الله ستكون في القائمة، لأنه بعد هذه هي السلسلة إن شاء الله سنذهب إلى الستاندر موديل بإذن الله تعالى. ستكون هي بعد الستاندر موديل، لأنه موجودة ضمن القائمة التي وضعنا في من القوائم السلسلة إن شاء الله بإذن الله تعالى.
very low, so the degree of divergence is either 0 or 1 or 2, so that means our divergences are polynomials of 0 degree, which means they are a constant, or they are proportional to one momentum, or at most they are quadratic in the momentum. So for example, for the photon or gluon self-energy.
طبعا هذه يتفق مع ماذا؟ يتفق مع معادلتي في كتابي الحلقة 54، حيث أنه التغير في الكتلة هي دالة في الطاقة، يمكن أن تكون دالة في المومنتوم، بحيث أنه دالة في الطاقة مقسومة على إكس. إكس هي تعتبر المسافة، مسافة التفاعل، أو أين يحدث التفاعل. إذا كان عميقا داخل مساحة مقطع التفاعل فإن كتل كبيرة تخرج، إذا كانت بعيدة كتل ثقيلة تخرج. هذا كله يتفق الآن مع ما يقوله هذا البروفيسور، يتفق معه تماما، وتخبرنا أن هناك أكثر من ذلك، أكثر مما يقوله هو، أكثر من ذلك، فحيث أنه تقول أن الأمر يتبع يعني في اللوب، وذكر في اللوب البروجكشن بالنسبة للبي يساوي 0، أو أي أننا لا نشعر بهذا الدايفرجنس، لكن في الحقيقة كله يظهر داخل اللوب وتترجم في الاختلاف في الكتل. يعني السيمتري بريك الذي يحصل يترجم في اختلاف في الكتل، لكن خارجا لا يخرج لنا مثل هذا. نحن نرى كتل مختلفة، ونرى أن هناك كتل عالية وكتل منخفضة جدا، وكأنه هناك جاب بين هذه الكتل. أين الكتل في النص؟ أين هي؟ يا إما عالية يا إما منخفضة، يعني هكذا. فهذه الجاب التي تحصل في الكتل هي نتيجة لهذا السيمتري الذي يحصل له بريكين، وهذا يمكن أن يترجم في مخالفة ما يقوله المحاضر، لكن لا نراه نحن، فقط نرى الكتل المختلفة، لأنه يترجم في هذا، لا يترجم في طريقة أخرى. ربما هناك طرق أخرى يترجم فيها، لكن الآن نحن ما نراه هو كتل مختلفة، لكن لا نرى شيئا آخر. فبالتالي السيمتري يعني محترم respected، ما عدا داخل الكتل التي تخرج من التفاعل.
It has the highest possible degree of divergence 2. Therefore, for that we know the divergence must be a polynomial of second degree in the momentum, and from the other blackboard we know it's transverse, and then we know exactly what the form of the divergence is. So let's write this maybe as an example. Sigma mu nu divergence at order n is a polynomial in second degree, let's say a times p mu p nu plus b times p square times g mu nu. Of course, we are also restricted by Lorentz covariance, and then we know that this is the only possibility that can appear. And p mu times sigma mu nu divergence is 0, and then we know that actually the structure of the divergence at the order n is given by common prefactor a times p mu p nu minus p square g mu nu. And then we know that this can be cancelled by this counter term that we have already derived, which had the result minus I times delta ZA times exactly this g mu nu p square minus p mu p nu. Okay, so we already showed that our renormalization transformation leads to a counter term structure like this, where the gluon self-energy counter term has a transverse part only, and the prefactor is a constant delta ZA. And now we learn from the main theorem of renormalization, the divergent part must have this structure. From the Slavnov-Taylor identity, we know transversality. In combination, we know that the divergence looks like that. Therefore, it is now established that it can be cancelled indeed by this counter term structure. That is how it works. And that is what you need to do in general for all green functions. We have now done it for the gluon self-energy, and you must walk through all the possible green functions that can exist in the theory and which can have possible divergences. And then for all possible green functions which can be divergent, you must show, using the same kind of argument, that the divergence has exactly the structure that can be cancelled by the counter term Lagrangian that we introduced last week. And that is true. So if you go through this analysis, then you see indeed that all ultraviolet divergences can be cancelled by the counter terms of the structure of our section 261. And that is then the induction step from n-1 to n. This is therefore possible, and that is the full proof of renormalizability of these Yang-Mills theories. Okay, that's the end. That's how it works. And so I would leave it at this sketch here. So to fill in the details, you would either on the one hand need to do the full proof of this main theorem of renormalization, which we did in the multi-loop lecture. And the other part is to go through this analysis here of applying the Slavnov-Taylor identity to the divergences and to show that that matches the counter term structure. And for that analysis, I will show you a few techniques, I think, in a few weeks from now, so that you see a little bit more in detail how one can proceed in order to do it. But we will first introduce a few other tools in between, so that this analysis is then a little bit more straightforward. And this analysis is exactly what was done by all those authors, and the most elegant form most likely is the one done by BRS using BRST symmetry. But essentially it was already done by the earlier works as well in a kind of similar logic. Yeah. IR is not covered by the theory of renormalization. So IR divergences happen once you go to specific external momenta, for example, on-shell external momenta. Then additional divergences can appear from long distances, and they have nothing to do with the renormalization procedure, and therefore they remain. They remain. So what is finite here? When I say green functions are finite, then I mean that the green functions are finite for generic external momenta, in particular for off-shell external momenta. So that means in momentum space you have analytic functions of your momenta for many, many different momentum variables. But if you go to special points in momentum space, then you get additional singularities which are not covered by that analysis. Of course, very important special points, namely physical special points, the infrared divergences appear exactly when you want to compute physical observables, so they are very important and also very, let's say, very tedious to deal with because they appear exactly in the important cases. Nevertheless, renormalization theory talks about the off-shell green functions for generic momenta, and first of all we need to establish that for generic momenta the green functions exist, and then we can perform limits and deal with the difficult limits in dedicated ways. Yep.
It is always that I find for every green function of the theory such a Taylor identity, such a restriction?
Obvious in a way, yes. Of course, it's not obvious that the analysis works and leads to this result. I wouldn't claim that this is obvious, but it's obvious that you can write down Slavnov-Taylor identities for all green functions because of this recipe. That is the recipe. And so, of course, here you can write down everything. And therefore, you get for every green function that you can possibly imagine, you can write down suitable Slavnov-Taylor identities, which will give you some restrictions. That is clear. And it's just then to be worked out what are exactly the restrictions and whether they are the ones that you need, but they are. Let me end with some comments. So as an extension, sometimes the Slavnov-Taylor identity may be broken in intermediate steps. Via the regularization procedure. If that happens, the Slavnov-Taylor identity is not automatically immediately valid, but then the Slavnov-Taylor identity must be restored by adding extra special counter terms. But once you have restored the Slavnov-Taylor identity by those extra special counter terms, then you can go on as before. And the final result.
هنا مقصوده هنا يمكن Slavnov identity يمكن كسرها في الانترميديت ستيبس هذه. هنا تدخل نظريتي، وهنا تدخل المفاهيم في كتابي الحلقة 54 و 55، وهنا يمكن للإنسان أن يبحث في هذا الأمر ويطور نظريته بناء على يطور له نظرية بناء على ما ذكر ما جاء في كتبه 54 و 55 و 53 أيضا، فيطور له نظرية يعني جميلة وأنيقة تتحدث عن بداية التفاعلات وحدوث التفاعلات وبداية الكون والمادة المظلمة الطاقة المظلمة، كل ذلك تدخل في هذه الآلية بإذن الله تعالى.
Is then also a fully renormalized theory which is finite. And where the Slavnov-Taylor identity is valid. And that is, for example, the case in the electroweak standard model with, let's say, rigorous treatment of gamma 5. Because as I told you, that we assume here at the moment that there is no gamma 5 in our theory, and that was the reason. So, but in all cases, regardless whether it's the more indirect or the direct case, the important outcome is that our renormalized theory has a valid Slavnov-Taylor identity. So we can use the Slavnov-Taylor identity then to constrain and understand the finite result of the green functions, which gives rise to the physical interpretation of the theory. And its free parameters are the ones of the classical action, because in the course of the renormalization procedure, never have been additional parameters been introduced. The parameters are always the ones from the classical action, because we just introduced the counter terms by the renormalization transformation of those original free parameters. That means the number of parameters that you need to measure until you are able to make new predictions is known, it is finite, and it is fixed. Doesn't depend on the order of perturbation theory. So these are the two important consequences for the interpretation. Okay, I would now go on with Slavnov-Taylor identities. After sketching the proof of renormalizability, we are not yet done with interpreting and establishing Yang-Mills theories. Namely, we also need to establish the physical properties of them, which are the properties that we discussed last week or 2 weeks ago, like unitarity of the physical S matrix, gauge independence of the S matrix, Lorentz invariance of S matrix elements despite not Lorentz covariant epsilon vectors, and so on. And those properties, we saw it at tree level, again depended on Slavnov-Taylor identities, but in that case, the Slavnov-Taylor identities were not restricting the divergences, but they were restricting finite parts and relationships between finite parts of green functions such that those physical properties would hold at the end. We looked at it only at tree level, where there are no divergences, but nevertheless, the identities were very important. So now we know that for the finite theory, the Slavnov-Taylor identities are valid at all orders, and so we have a chance to basically repeat the discussion of those physical properties at all orders. And that is what I want to do to complete this section. And so first let me tell you a little bit about Slavnov-Taylor identities in general for S matrix elements. And then we can sketch the applications to the points that I mentioned. So far, we looked at Slavnov-Taylor identities for green functions, where all the PIs were arbitrary, so-called off-shell. And that is obviously useful for renormalization. And in general, it's useful to study general properties. But now let us look at S-matrix elements. So we specialize the Slavnov-Taylor identity to on-shell quantities, and in particular to the S-matrix. And then we can study properties like the ones I just mentioned. That was section 252, 253 on the unitarity of the physical S-matrix or the gauge independence of the physical S-matrix. Okay, and actually maybe a question. I had prepared a few remarks on the relationship between green functions and S-matrix elements in general, like the so-called LSZ reduction. Do you want me to discuss that, or should we skip it? Since we didn't do it in Quantum Field Theory 1 last semester, maybe I should discuss it. I feel that would be important, but it takes a little bit of time. And let me do it by an illustration, not with a general derivation, but let me just illustrate the point. So let us look at tree-level cases. That was what we studied in Quantum Field Theory 1b, in other words, in the last semester. There we had, for example, such a process like Compton scattering, which consists of such Feynman diagrams here, this one and the one with crossed legs. And I told you, and we derived completely how we obtain the S-matrix and T-matrix element for such a process. And in words, the recipe was to have external wave functions for the external particles, like spinors U bar and U, and polarization vectors epsilon mu for the external photons. And then we have the usual Feynman rules for the inner line, like 1 over p slash minus m, and for the vertices gamma mu, gamma nu, and so on. So we derive the Feynman rules for this. Let me do a simpler example. For example, this process, just photon going to E plus, E minus, in quotation marks, because the photon cannot decay into E plus, E minus in reality, but let's just pretend it could. Then the Feynman rules for this would be the following. We have a spinor U bar for the outgoing electron, U bar with the argument P prime. Then we have the vertex Feynman rule minus I EQ gamma mu for the vertex here, and we have a spinor U of P for the outgoing positron, and or let's say V of, let's do it correctly, V of P like this. And we have a polarization vector epsilon mu of K for the incoming photon. Okay, so that would be the Feynman rule for this S-matrix element, if it were a physical process. Okay, now let's compare it to a green function. Let's compare it to a green function psi, psi bar, and a mu. Let's say a mu. Fourier transformed such that here, let's say, okay, let's first write down the Feynman diagrams. What are the Feynman diagrams for this green function? The Feynman diagram for the green function, the simplest one would of course be the same. So here we have a Feynman diagram for that green function. Namely, the green function corresponds to all Feynman diagrams with external fields A, psi bar, psi. So here we have the external A nu. Here we have the external psi bar. And here we have the external psi. Now what is the difference between that Feynman diagram and this one? I try to highlight the difference graphically by writing dots at the end of those lines here. The difference is that here this Feynman diagram contains Feynman rules for the external lines, and the external lines in this Feynman diagram, they are simply propagator Feynman rules. So here I get the following result for this diagram, namely I get, let's start here with this line, I get a Feynman rule for this line, which is simply I divided by p prime slash minus m. This is just a propagator Feynman rule. Then I have this vertex here, minus I eq gamma mu. Then we have this propagator Feynman rule, I divided by p slash minus m. And here we have a propagator for the photon field, which connects here the A mu with an A nu photon field. So we have a propagator minus I divided by k square times g mu nu minus k nu divided by k square times 1 minus psi. So this is the value of that Feynman diagram for a green function. And now the point I want to make is to analyze the difference. What is the difference between the Feynman diagram for such a green function and the Feynman diagram for a T matrix element? And you see it. The difference is that for the green function we have propagators for the external lines, namely here for the 3 external lines we have 3 propagators. Here the electron propagator, positron propagator, photon propagator, and instead in the S matrix we have spinors or polarization vectors for the external states. But the vertex for the inner vertex is the same. So and that is the general relationship. You can go from green functions to the S matrix by stripping away the external propagators and replacing them by those spinors or in general wave functions for the external particles. That is just the difference. And then also the green function here is defined for arbitrary external momenta. The momenta do not have to be on shell. They can be anything. But if you put the external momenta to an on-shell value, for example, photon k square equals 0, what happens with the green function if k square goes to 0? Johannes? You can look at all these different factors until you see something that happens for k square going to 0. It is divergent. What happens if p square goes to m square? It's not so easy to see, but this thing here is of course the same as p slash plus m divided by p square minus m square, and so it is also divergent. So if the external momenta become on shell, the same for p square going, p prime square going to m square, then this is divergent. So this green function has a pole if k square goes to 0. It also has a pole if p square goes to m square, and it has a pole if p prime square goes to m square. So these general green functions, they have poles whenever an external momentum goes to an on-shell value equal to the mass of the respective particle. So those green functions have poles. And so the relationship between the green function is now a little bit more tricky. So first of all, the S matrix is calculated for on-shell momenta. So here p square is equal to m square, p prime square is equal to m square, k square is equal to 0. and exactly those values are impossible to take in the green function because of the poles. So therefore the relationship is you strip away the external propagators. After doing that, the green function, the remainder is finite if you go to the poles. So then you set all the momenta to the on-shell values, and then you multiply with those external wave functions, and then you get the S matrix. That is the recipe going from here to here. Away the external propagators. After doing that, the green function, the remainder is finite if you go to the poles. So then you set all the momenta to the on-shell values, and then you multiply with those external wave functions, and then you get the S matrix. That is the recipe going from here to here. So remove external propagators, on-shell limit, multiply.
طيب هنا في نظريتي ما معنى أن الجرين فانكشن أو نحن نعوض ونذهب إلى البولز أو الجرين فانكشن لها بولز. طبعا قلنا أنا الجرين فانكشن هي عبارة عن معادلة للطاقة، ومعادلة للطاقة إذا حسبتها هي عبارة عن الطاقة التي توفرها الجاذبية بالنسبة للطاقة المطلوبة للكون كله. الطاقة المطلوبة للكون كله هي 10 أس 123. فالطاقة توفرها بالجاذبية يجب أن تكون أقل من 10 أس 123، وإذا فاتت فإن الكون الفضاء ثنائي الأبعاد سيفعل عملية الاندفاع النفسي مباشرة. طيب، وهذا ما يحدث الثقب الأسود الذي يعتبر أضخم وأثقل الأجسام، حيث أن طاقته التي توفرها الجاذبية أقل من 110 أس 123، وإذا تناول وجبة وفاتت هذه النسبة أو قاربت منها فإن الفضاء ثنائي الأبعاد يفعل آلياته ويطرد الطاقة الزيادة أو الكتلة الزيادة بواسطة ال5 آليات والتي معروفة من خلال السلسلة، وهي توسيع الفضاء لأن هي كثافة كتلية، السبين، طرد الطاقة، طرد الكتلة، الموجات الجاذبية. إذا كانت وصلنا حتى الحد للبولز بالنسبة للجرين فانكشن، فإن هذا يعني أن طاقة الجاذبية فاتت الطاقة المطلوبة للفضاء ثنائي الأبعاد غير متناظر، يعني فاتت 10 أس 123. هنا سيفعل الفضاء ثنائي الأبعاد آليته ويدافع عن نفسه، وبالتالي ما يحصل في التفاعلات دون ذرية أنه نجد أن التفاعل مستقر ولا ينفجر مثلا ولا يحدث انفجارات ضخمة. فهذا يعني أن الفضاء الثنائي الأبعاد هو المسيطر على الفضاء. الانتقال من الجرين فانكشن إلى الفايمان فايمان رولز، هو ذكر أن نوصل هذه القيم إلى البول، نوصل الجرين فانكشن إلى البول، حيث نضع ام بي تربيع يساوي ام تربيع، أو نجعل كي يساوي 0، نصل إلى البول. إذا وصلنا إلى البول هنا الجرين فانكشن تساوي الوحدة، ساوت الوحدة، فإن الفايمان رولز ستعمل في هذه، لأنه سنعوض بعد ذلك البروباجيتور اكسترنال البروباجيتور بالويف السبينر وما إلى ذلك. في هذه اللحظة هنا نعبر عن فايمان رولز كما ذكرنا مرارا وتكرارا بأن هي الطاقة المطرودة من التفاعل، يعني أن ما ذكره البروفيسور أن نوصل للانتقال من الجرين فانكشن interaction in green function إلى الفايمان رولز، يجب أن نوصل الجرين فانكشن إلى البول، بحيث أنه نجعل ام سكوير يساوي بي سكوير وهكذا. هنا مباشرة عوضنا بأن وصلنا الجرين فانكشن أو وصلنا طاقة الجاذبية، حتى 123. ماذا يفعل؟ الفضاء صناعي الأبعاد سيطرد هذه الطاقة، وبالتالي ستتحول الفايمن رولز إلى طاقات مطرودة من التفاعل. وهذا ما ذكرته من بداية السلسلة، أن فايمن رولز ما هي إلا طاقات مطرودة من التفاعل. هذا ما ذكرته أنا كيو إي دي، بالرغم من التشابه بينه وبين الريمان تنسور وهذا كل هذا التشابه، ما هي لا تعبر إلا عن طاقة مطرودة من التفاعل. فالفايمن رول يعبر عن طاقة مطرودة من التفاعل، وهذا هو الدليل آخر على صحة كلامي.
With wave functions. Gives you the green function, produces then such a T-matrix element. Okay, that is the recipe. And this recipe, yeah. It is a recipe, right? So you strip away the propagators. After stripping away the propagators, you remain with this. And then you multiply with wave functions. So you multiply with u bar and u and epsilon. That is the recipe. It's a recipe. What it gets us is it goes from here to here. You start by having a green function, but you want an S-matrix element. So you ask, how can I obtain an S-matrix element if I have only a green function? That is a good question, because now we have studied renormalization of gauge theories and we have cancelled divergences and so on. So all we know are green functions. We do not yet know S-matrix elements. But green functions we know. The renormalization that we have just sketched 5 minutes ago tells us that we know for sure green functions exist. Therefore, green functions for us are now the more basic building blocks. But of course, we want S-matrix elements. And so your question should be, how can I get S-matrix elements if I have green functions? And so, therefore, I wrote down a tree-level example which you can understand from last semester's lecture. And then you see these three differences. Here there are external propagators. Let's get rid of them. Then the momentum must be on shell. After getting rid of the propagators, we can set the momentum on shell. And then we are still not there, but we need to multiply with those external wave functions. And if we do all these three steps, then we go from a green function to an S-matrix element. So you wondered where the wave functions come from, or what? Yes. And strip away, you can mathematically formulate it exactly by multiplying with the inverse of a propagator, because there is a precisely known Feynman rule for every external propagator, and of course it's a well-defined calculation to multiply with the inverse. You multiply with the inverse, and then you take the on-shell limit, and then that limit will exist, and it gives you, in this case, just this result. Afterwards you multiply with the wave function. You also had a question? Yeah, in some sense, if you would have a theory where somebody gives you only S-matrix elements and you might know them as numbers, then it's a little bit difficult and tricky to go from these numbers to the green functions, because those numbers would be defined after contracting with the wave functions. That of course reduces the information that you have, and you only know it for on-shell momenta. So you would have to kind of extrapolate to off-shell momenta, and that might not be unique. And actually it is not unique. So you might describe the same S matrix from different green functions. In fact, that is also a possibility that is sometimes made use of. And so the opposite way is not unique. But of course, in a way, it is possible because you can kind of interpret green functions as generalized S matrix elements of some theories, but it is not a unique procedure to do that. But if you have green functions in a theory, then you can construct an S matrix element. And so what I have told you now is an observation that is true at tree level, and the so-called LSZ formalism and LSZ reduction theorem, which is a theorem of axiomatic quantum field theory, tells us that this same recipe is actually true exactly, non-perturbatively, for arbitrary quantum field theories. And it works if you have green functions given at all orders, let's say. Then the essentially same recipe brings you from those green functions of some renormalized theory to the S matrix elements of the same theory. And so that is the way how we can define S matrix elements at higher orders for generic quantum field theories, even without using perturbation theory. Because in our quantum field theory 1 lecture, we used the so-called time-ordered perturbation theory to derive the Feynman rules for S matrix elements, and we obtained that result. If one would apply the same strategy at higher orders, one would still get some results, but it would always remain perturbative. It would agree with what I tell you now, but the LSZ formalism is even valid non-perturbatively. So let me just quote the LSZ reduction statement, which is essentially this recipe. And we derived this in quantum field theory 1a in section 4. So, and let me just write down a simple graphical version which explains the recipe. Namely, if you have a TFI matrix element, then this is given by, let's say, the appropriate green function. By appropriate green function, I mean, of course, a green function which has the correct structure of external legs, external particles, so that you have a chance of describing with that green function the process that you are interested in. Then you amputate the external legs, and then you multiply with the following, say 1 over square root of that should be a curly z square root times wave functions of all external particles. So it is exactly the same recipe as here. The only difference is this 1 over square root of curly z, which is the following, where 1 over square root of curly z is determined by the following. Let me write it down for scalar fields. Namely, you take the full green function of such a scalar field, and I take a scalar field because then we do not have P slash or such a complicated Lorentz structure which I would need to write down. Then the Lorentz structure is simply that this green function behaves like 1 over P square minus M square plus I epsilon. And the tree level propagator for a scalar field would be just I divided by that, right? I divided by p square minus m square plus I epsilon. And at all orders, such a two-point function for a scalar field can be written like I times square root of curly z divided by p square minus the physical mass square m square physical plus I epsilon plus additional terms without pole at p square equal m physical square. So that is the general structure of such a two-point function. At tree level it is just I divided by a pole. At higher orders it still has a pole. Maybe the position of the pole is shifted from the tree level mass to some new mass which we then call the physical mass, but it still has a pole, or it might have a pole. The pole position has shifted, the residue has shifted, and the residue at the pole is now called curly z. In some cases it might even become zero, but in general the residue is called z, and of course the modification also leads to terms which have no pole, but around the pole we can always approximate such a two-point function in this way. So compared to tree level, shifted residue and shifted position of the pole, and the residue is called curly z, and this has the interpretation of a normalization factor. So this gives the normalization of the external fields, and we need to divide by that normalization factor in order to have proper normalization of our matrix elements if we want to interpret them as probability amplitudes. So they need an absolute fixed normalization, and that normalization comes from here. So that is the outcome of the LSE theorem, which we derived in that lecture. It is non-perturbatively valid, and it boils down to that recipe that we have just observed at tree level. And so here, another answer to your question, where do the wave functions come from, is the proof of this LSE theorem. It produces, after a certain series of steps, exactly this result here. The proof is not totally simple, but also not prohibitively difficult. Okay, now we have not yet discussed Lyapunov-Taylor identities for the S matrix. We've only discussed the S matrix, but now you see what becomes possible. Namely, if you have green functions and you can construct S matrix elements just from green functions by that recipe, it enables you also to derive Lyapunov-Taylor identities for the S matrix by using the Lyapunov-Taylor identity for the green functions and applying the same recipe. In this way you will automatically obtain some relationships for S matrix elements. And those are Lyapunov-Taylor identities for the S matrix. And let's just see how much we can. Okay, we cannot do very much. But let me write down the general structure, and then let's discuss whether we can go on in the afternoon or next week. So let me introduce a notation which shows you also what we will be able to do. So notation for the LSE reduction. And for simplicity in the following, we simply assume that this curly z is equal to 1. Then we do not have to carry it around in equations, and it is no loss of generality to assume it is 1, because you can always renormalize your fields in such a way that the two-point function here has residue 1. And so let's assume it, and it makes the equations a little bit simpler. So then we introduce the following notation. So here some notation for a green function, and then we write it like this: amputated and on shell, and that is basically applying the recipe above. So we take a green function, so let's write it down. It is defined as taking the green function in momentum space, and then we multiply with the inverse propagators. Which is the recipe to cancel the external propagators or to strip them away, but mathematically we can really multiply with the inverse. Then after multiplying with the inverse, we take the limit where all the external momenta pi square go to the corresponding physical masses where the external propagators have poles. And at the end we multiply with wave functions. However, I put the last point in bracket if, let's say, needed. The last step will be sometimes omitted in order to have more general relationships, but we will see that. The main point is that we amputate the external legs and go on shell, and this is a recipe which leads you from the green functions towards the S matrix. And now, of course, you can sort of sense what we will do later. Namely, we take a Slavnov-Taylor identity which gives us a relationship between different green functions. Sum of green functions is 0. Then the entire equation is of course valid for all momenta. So we take it, amputate and go on shell, and then we derive an identity as a corollary from that. And that identity will have special properties. There will be dramatic simplifications, and therefore it's important and worthwhile to study those resulting identities separately. And those are the identities which one needs to look at unitarity of the physical S matrix and so on. Okay, so that ends our lecture, but there is a question. Yes. 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 Yes, indeed. Yes. Yes. Not all of the resulting identities will be interesting, however, but we will see what kind of simplifications will emerge. And yeah. Okay, let's continue with our lecture.
تمام، خلاص أنا سأنهي هذه الحلقة على كده، وسأسجل فيديو جديد إن شاء الله الحلقة القادمة.